We've seen how associated with any complex number is a modulus and an argument. In fact, using those two numbers, it's another way to describe a complex number. Instead of in its Cartesian form x plus iy, we can formulate what's called the modulus argument form of a complex number. Let's consider this as follows. If we have a number z in the complex plane, we've seen that if we draw the line from the origin to the complex number, we call the distance to that the modulus and angle made with the real axis the argument. Now, using these two numbers, it's just a matter of trigonometry to see that along the real axis we have a distance z cos theta from the origin, and along the imaginary axis we have a distance z sine theta. So the real part of z is the modulus of z cos theta, and the imaginary part of z is modulus of z sine theta. Therefore I can write z as the modulus of z times the number cos theta plus I sine theta. This is known as the modulus argument form of the complex number. So if I have a number like 1 plus I over root 3, then I can rewrite this in modulus argument form. If I just draw a quick diagram, then I can read off what the principal argument is. So because tan theta is 1 over root 3, theta is pi by 6, the modulus of z is just the square root of x squared plus y squared, and so therefore an equally good form for the complex number. Now, of course, you can evaluate the cos and the sine of pi by 6 and get back where we started, so it perhaps seemed a little bit trivial to do this, but it turns out there's some very nice properties that come with writing a complex number in its modulus argument form. Let's have a look at multiplication and division by complex numbers. Using the modulus argument form, we can see that this gives us a geometrical way to visualize what's going on. Let's take two complex numbers, w and z, and write them in their modulus argument form. What I'm going to do is multiply them together and then simplify. So if I gather the real and imaginary parts separately, I have cos theta cos phi minus sine theta sine phi, where the minus comes from the I squared factor, gathering the imaginary terms. And now here's a really neat thing. I can now use my sum and difference formulas from trigonometry in order to rewrite this as. So it comes out in exactly modulus argument form, with a modulus which is the product of the two moduli, z and w, and an argument which is the sum of the two arguments of z and w. So that's a really neat fact. So it tells us that when I multiply two complex numbers together, I change the length according to the moduli of z and w, and the argument is a rotation in the complex plane. So if I have a number z and a number w, then I can figure out where z times w is, because it's going to have an argument of theta plus phi. So if I add on theta to phi, it's going to lie somewhere on this line, and to find out where on this line, I need to multiply the moduli of z and w together. Now, because these numbers are larger than 1, that's going to be further away from the origin, and so I can expect that z times w will be over here somewhere, lying on this line from the origin. Now there's a few important examples. Consider the number minus z. Now minus z is minus 1 times z, and minus 1 in modulus argument form has a length of 1 and an argument of pi. So this means that to multiply by minus 1, we rotate the number by pi. Similarly, multiplication by I is a rotation by pi by 2 because the argument of I is pi by 2. So if I have a number z, minus z is a rotation by pi, and I times z is a rotation by pi by 2. So a rotation by pi by 2 gives me I times z, and a rotation by minus pi by 2 gives me minus I times z. So multiplication is kind of neat in modulus argument form. What about division? Well, this is also extremely interesting. Consider 1 over z. So I write down 1 over z in its modulus argument form, and what I'd like to do is simplify the denominator. Now 1 over modulus of z is just a real number, so I'll just leave that as it is. This number here can be simplified as follows. And then the denominator, gathering everything together, gives cos squared plus sine squared theta, which is just 1. So we have, now in order to see what this is in terms of a modulus argument form, cos of minus theta plus I times sine of minus theta. So division by a complex number then is division by the moduli get divided by the length of z, and a rotation by minus theta, so a clockwise rotation. So that's a really important result. And in fact, let's just come back to this number in general. This is a really important way to write down a certain class of numbers. Let's consider all complex numbers which can be written in the form cos theta plus I sine theta, where theta is a real number. In this case, the modulus of z is equal to 1. So all of these numbers then lie on the unit circle. Now it turns out they have a very special property. If I take this number and raise it to some integer power n, then this is equal to cos n theta plus I sine n theta. And it arises upon application of the cosine sum rules that we saw before. This tells us that to raise a number on the unit circle to some power, I rotate it by n theta around the unit circle. So this is a really neat result, and it's known as the Moivres theorem, and plays a key role in establishing the exponential function for complex numbers shortly.